Hello and welcome to AI Fundamentals course, Fundamentals of Artificial Intelligence. My name is Andrew Cronoff and I'm a Microsoft Technical Trainer or MTT with Microsoft. Let's get started with session one. In our first session, we're going to create the foundation of knowledge in our AI. We're going to discuss how the AI models are created and the wide variety of tasks we can accomplish with them. And then we're going to discuss how we can access those tools in Azure and help us create our own AI models, and then how to rapidly add AI to our applications and solutions with the pre-built AI models. So let's get started. Our session is divided into three parts, or this part of our session, and it's the fundamental AI concepts, and then we're going to talk about the fundamentals of machine learning, and then the fundamentals of Azure AI services. In the first section, we're going to answer three big questions about AI. We start with what is AI? This gives us a baseline for the rest of the sessions. And then what are some common AI workloads and understanding where AI fits in the organization? And how do we add AI workloads in a responsible way? So here we're going to talk about the tools we use that guide us and help us be responsible in working with AI. Artificial intelligence is when machines, like computers, can do things like normally require human intelligence. Things that most humans do daily, often subconsciously. We make predictions or we recognize patterns and we use information that's available with our experience to guide us. We intuitively know when something isn't quite right or doesn't fit a pattern. Humans with vision use sight to experience the world visually, identifying options and written words around us. And we communicate by writing and speaking and engaging in dynamic conversations, responding appropriately. We can extract information from multiple sources to extend our knowledge. So here we're listing common workloads individually, but it's important to understand that we will often combine workload types and some will overlap with the capabilities, and that is expected. So for example, imagine a conversational AI solution that uses a chatbot to process an auto insurance claim. The bot relies on some natural language processing capabilities to make sense of input, such as I want to submit a claim, which can be typed or spoken. The chatbot may allow the user to send a photograph of the damaged vehicle and use computer vision to assess the damage and apply a machine learning model to predict likely repair costs. The bot might also use anomaly detection to identify potentially fraudulent claims. And finally, the claims data, including forms, photographs, and other artifacts, might be indexed to extract insights and create a searchable knowledge store to help manage future claims. At Microsoft, AI software development is guided by a set of 6 principles for responsible AI. Let's go through some scenarios that illustrate each of these principles of fairness. First, we'll start with fairness, which is an AI system should treat all people fairly. For example, suppose you create a machine learning model to support a loan approval application for a bank. The model should make predictions of whether the loan should be approved without incorporating any bias based on gender, ethnicity, or other factors that might result in an unfair advantage or disadvantage to specific groups of applicants. Azure Machine Learning includes the capability to interpret models and quantify the extent to which each feature of the data influences the model's prediction. This capability helps data scientists and developers identify and mitigate the bias in the model. Reliability and safety is another key concern. Our AI systems should perform reliably and safely. For example, consider an AI-based software system with an autonomous vehicle or a machine learning model that diagnoses patient symptoms and recommends prescriptions. Unreliability in these kinds of systems can result in substantial human risk and loss of life, potentially. AI-based software application development must be subject to rigorous testing and deployment managed processes, and that ensures that they work as expected before release. And privacy and security is obviously a huge concern. AI systems should be secure and respect privacy. The machine learning models on which AI systems are based rely on large volumes of data which may contain personal details that must be kept private. Even after the models are trained and the system is in production, it uses new data to make predictions or take action that may be subject to privacy or security concerns. Inclusiveness. All AI systems should empower everyone to engage people and engage all people. So AI should bring benefits to all parts of society, regardless of physical ability, gender, sexual orientation, ethnicity, or other factors. And transparency. All of our AI systems should be understandable. Users should be made fully aware of the purpose of the system and how it works what limitations may be expected. Finally, we have accountability. People should be accountable for AI systems. Designers, developers, and AI-based solutions should work within a framework of governance and organizational principles that ensure the solution meets ethical and legal standards that are clearly defined. In this next section, we will discuss how the AI models we use are created and what tools are available to create your own models. The fundamentals of machine learning is in 5 parts. What is machine learning? Types of machine learning, model training and validation, what is deep learning, and what is Azure Machine Learning. So machine learning can be described as some variation on the following 4 steps. The training data consists of past observations in most cases. The observations include the observed attributes or features of the thing being observed and the known value of the thing you want to train the model to predict, and we call that the label. In mathematical terms, you'll often see the features referred to use the shorthand variable names x, and the label is referred to as y. Usually, an observation consists of multiple feature values, so x is actually a vector or an array of multiple values, such as x1, x2, x3, etc. An algorithm is applied to the data to try to determine a relationship between the features and the label, and generalize that relationship as a calculation that can be performed on x to calculate y. The specific algorithm used depends on the kind of predictive problems you're trying to solve, but the basic principles is to try to fit the data to the function in which the values of the features can be used to calculate the label. The result of the algorithm is a model that encapsulates the calculation derived from the algorithm as a function, and let's call it f. It's f for function. So mathematical notation, y equals the function of x. Now, the training phase is complete. The training model can be used for inferencing. The model is essentially a software program that encapsulates the function produced by the training process. You can input a set of feature values and receive as an output the prediction of the corresponding label. Because the output from the model is a prediction that was calculated by the function, it's not an observed value, and you'll often see the output from the function y hat as shown on the slide. Supervised machine learning is a general term for machine learning algorithms in which the training data includes both the feature values and the known label values. So supervised machine learning is used to train models by determining a relationship between the features and the labels in past observations, and then predict them for the future cases. So regression is a form of supervised machine learning in which the label predicted by the model is a numeric value. For example, the number of ice creams sold on a given day based on the temperature, rain, and wind speed. The selling price of a property based on its size in square feet, the number of bedrooms it contains, and socioeconomic metrics for its location. Or the fuel efficiency in miles per gallon of a car based on its engine size, weight, width, height, and length. Classification is a form of supervised machine learning in which the label represents a category or a class. There are 2 common classification scenarios. So binary classification, the label determines is the item there or is it not there, an instance of a specific class. So to put it another way, the models predict one of 2 mutually exclusive outcomes. For example, whether a patient is at risk for diabetes based on clinical metrics like weight, age, glucose level, etc. So they either are or they are not. Or whether a bank customer will default on a loan based on income, credit history, age, and other factors. Or if a mailing list customer will open a positively marketed item to their demographic based on their past purchases. In all of these examples, the model predicts a binary true or false, positive or negative, yes or no type of answer for a single possible class. Multi-class classification extends the binary classification to predict a label that represents one of multiple possible classes. So, for example, the species of a penguin, we have, Adelie, Gentoo, or a chinstrap, based on its physical measurements. The genre of a movie, comedy, horror, or romance, or science fiction based on the cast, the director, and the budget. In most scenarios, this involves a known set of multiple classes, and multi-class classification is used to predict mutually exclusive labels. So for example, a penguin can't both be a Gentoo and Adelie. However, there are also some algorithms that you can use to train multi-label classification models in which there may be more than one valid label for a single observation. So for example, a movie could potentially be categorized as both science fiction and a comedy. Unsupervised machine learning involves training models using data that consists only of the feature values. So there is no known labels. Unsupervised learning algorithms determine relationships between the features of the observations in the training data. Clustering is the most common form of unsupervised machine learning. A clustering algorithm identifies similarities between observations based on their features and groups them together in discrete clusters. So an example of that would be similar flowers based on their size, the number of leaves, the number of petals, or identifying a group of similar customers based on their demographic attributes and purchasing behavior. In some ways, clustering is similar to multi-class classification in that it categorizes observations into discrete groups. The difference is that when using the classification, you already know the classes in which the observation is belonging to. So the algorithm works by determining the relationships between the features and the known classification label. In clustering, there's no previously known cluster label. The algorithm groups the data on the observations purely on similarity features. In some cases, clustering is used to determine the set of classes that exist before training a classification model. So for example, you might use clustering to segment your customers into groups and then analyze those groups and identify the categories of different classes. So high value, low volume, frequent small purchaser, that type of thing. You could then use your categorizations to label the observations in your clustering results and use that labeling data to train classified models that predicts to which customer category a new customer might belong. Now let's relate this to X and Y from the previous slide. In the ice cream sales scenario, our goal is to train a model that can predict the number of ice cream sales based on the weather. So the weather measurements for the day, temperature, rainfall, wind speed, and so on, would be in the features X, and the ice cream sold on each day would be the label Y. In the medical scenario, the goal is to predict if a patient is at risk of diabetes based on their clinical measurements. The patient's measurements, weight, blood glucose, etc., are the X, and the likelihood of diabetes would be example 1 or 0, or no risk would be the label Y. In the Antarctic research scenario, we want to predict the species of a penguin based on its physical attributes. The key measurements, the length of the flippers, width of the bill, and so on, are the features X, and the species, for example, Adele or Gentoo, would be the label Y. Training is the heart of machine learning. It's where we teach the model to find the patterns in the data. We use an algorithm to adjust the model until the data fits as well as possible. After training, we have the model that we can test. So we use some of the data that we set aside at the beginning, and we call that data validation data. That's to test how close our model's prediction labels are to the actual labels. In the case of unsupervised learning, where we don't know the actual labels, we measure how well the model's prediction are predicted on the labels. So we're separating clusters. There are many types of evaluation metrics. The important thing to remember is that the goal of machine learning is to find a model that gets as close as possible to predicting the actual label. The best model can still have a margin of error. Deep learning is an advanced form of machine learning. It tries to emulate the way the human brain learns. The key to deep learning is that the creation of an artificial neural network. And this simulates the electrochemical activity in a biological neurons by using mathematical functions. So the artificial neural networks are made up of multiple layers of neurons, especially defining a deep nested function. So this architecture is the reason the technique is referred to as deep learning, and the models produced by it are often referred to as deep neural networks, or DNNs. You can use deep neural networks for many kinds of machine learning problems, including regression and classification, as well as more specialized models for natural language processing and computer vision. To better understand how deep neural network models work, let's explore an example in which a neural network is used to define a classification model for penguin species. So the feature data X consists of some measurements of a penguin. Specifically, the measurements are the length of the penguin's bill, the depth of the penguin's bill, the length of the penguin's flippers, the penguin's weight. And the label we're trying to predict, Y, is the species of that penguin, and there are 3 possible species it could be: Adélie, Gentoo, or Chinstrap. The process for inferencing a predicted penguin class using this network is The feature vector for a penguin observation is fed into the input layer of the neural network, which consists of a neuron for each x value. So remember, those are the input values. So in this following example, the x vector is used for the input. They're showing like 37.3, 16.8, etc. The function for the first layer of neurons each calculate a weighted sum by combining the x and the w, the weight. So each neuron in a layer is connected to all of the neurons in the next layer. The results of each layer are fed forward through the network until they reach the output layer. The output layer produces a vector of values, in this case using a softmax or similar function, to calculate the probability distribution for the 3 possible classes of penguin. In this output vector is 0.2, 0.7, and 0.1. The elements of the vector represent the probabilities for classes 0, 1, and 2, our 3 penguin types. The second value is the highest, so the model predicts that the species of the penguin 1 is Gen 2 in this case. The model learns the appropriate weights by iteratively passing the training data through and evaluating the predicted probabilities for each class against the known class label. So the weights are adjusted in each iteration to reduce the amount of error or loss between predicted probabilities. For example, the 0.2, 0.7, 0.1, and the values that represent the actual class label, for example, 0.0, 1.0, and 0.0 for class 1 Gen 2. Microsoft Azure Machine Learning is a cloud service for training and deploying managed machine learning models. It's designed to be used by data scientists, software engineers, DevOps professionals, and others to manage the end-to-end lifecycle of machine learning projects, including exploring data and preparing it for modeling, training and evaluating the machine learning models, registering and managing trained models, and deploying trained models for use by applications and services. Reviewing and applying responsible AI principles and practices. Once you've provisioned an Azure Machine Learning workspace, you can use it in Azure Machine Learning Studio, a browser-based portal for managing your machine learning resources and jobs. And in that Machine Learning Studio, you can, among other things, do the following. You can import and export data. You can create and use compute resources. You can run code in notebooks. You can use visual tools to create jobs and pipelines. You can also use automated machine learning to train models, view the details of those trained models, including the evaluation metrics, the responsible AI information, and training parameters. You can also deploy the trained models on request and use batch inferencing. You can import and manage models from a comprehensive model catalog as well. In this demo, you will see how machine learning features can be used to train a machine learning model and to make predictions. Here we are in Azure, and I'm creating an Azure Machine Learning resource. I'm going to put it in my resource group, which is going to act as a lifecycle container for all of the things that I need for my tool. I'm going to go ahead and set my configuration, and then I'm going to do a validation and create step here. All right, there's my machine learning resource. And what I want to do is launch the studio. This is where the machine learning work is going to take place. And so we're going to do an automated machine learning step here, and we're going to do a regression count. So we're going to go in and create a new job, and we're going to fill out some configuration before we get to see what's going on. So we're going to give our job a name, and then we're going to set up our experiment name and our description. So as you go through here, you can go through, you can see the different configurations that you can create here. We're going to choose regression to get different results, or to, depending on what your data requires, to set things up. All right, so we're going to create a data asset. We're going to give it a name and a short description. All right, this is going to be our bike rental data, and I'm going to then get this and choose the correct one that I want. And we're going to approve our data set. And there's the path that we do for the upload, and we're going to go ahead and upload from folder now. So we're going to find our bike data, upload all of it, and give that a minute to do that. All right, looks like it's done. There we have our data. We're going to go next. So we've imported the data. We've connected it to our job. All right, we're going to make a couple settings here. So we're going to go ahead and we're going to choose the random forest and the light GBM. There we go. So there's different models for our base that we can use, and we're going to go ahead and set some other configurations here. The important thing is that you can see how powerful the tool is and how much control we have over each of our data imports and the variety of ways that we can choose different base models and then choose different fine tunings. All right, we have everything set up. The status is complete. We've done our data ingestion. We're going to go through it and we can see our details of what's happening. If we go to our metrics, we can see our predicted tree and our histogram there. Okay, so now we want to deploy the model. So we've gone through, we've trained it, our data's in there, we've given on our parameters. It should give us now a nice regression number. So that regression was on that the prediction tree. It should follow along that line. We're going to go ahead and deploy our model to an endpoint, and now we're going to go to that endpoint and see what's there. So we have our endpoint, it's succeeded. We're going to test it now. And to do that, we're going to put in some categories that work with our data. And there we go. We have a nice regression that falls on our line. And it's just that easy to test it and make it available. That's been a quick tour of Azure Machine Learning. The Fundamentals of Azure AI Service section is in 3 parts. Azure Basics, a brief introduction to Microsoft Azure. AI services available on Microsoft Azure, and Azure AI services. Microsoft Azure is a hyperscale cloud service, and what that means is cloud users can deploy resources, and there is quite a reserve of capacity in the cloud for scaling and expanding. You will see in our Azure portal in our demonstrations. In the portal is where we can view and create, update, and delete all of our resources, and many of the ways of connecting to Azure exist. We're going to show you the portal, but you can use the command line. There's various deployment tools and all the ways that you can connect. And you're going to see our resources when we create them are going to be in what are called resource groups. Resource groups are lifecycle containers, and we do all of our work inside the resources themselves, either right there in the portal or, as you'll see with AI, often in a studio environment that's designed specifically for that resource. We have already seen Azure Machine Learning and how machine learning forms the foundation of AI's predictive capabilities. Next, we're going to look at Azure AI services in the areas of Azure AI Vision, including the features image analysis and face and optical character recognition. We're going to look at Azure AI Language, including the information extraction, text summarization and classification, question and answering, and conversational language understanding. Azure AI Speech, including text-to-speech and speech-to-text, Azure OpenAI, and Azure AI Search. It's worth spending a little more time examining Azure's AI services as they illustrate a pattern that is common for many AI app scenarios in Azure. To use Azure AI services, you must provision a resource in your Azure subscription. This can be a standalone resource, which is like a service-specific resource. AI Vision is a good example of that, or the general Azure AI Services multi-service account. That resource encapsulates multiple services, and using the standalone is going to give you the ability to save costs and work specifically with that, and has its own security and its own rules. And outside of that, when we're using the larger ones, you'll be able to combine them and get that savings. AI services in a single Azure resource can be centralized for the management. So regardless of the type of resource you use, the client applications will consume that service that it provides by connecting to a REST endpoint. So it's an HTTPS address to which they can submit requests using resource-specific keys for authentication or managed identities. Now let's take a look at Azure AI services in Azure. All right, here we are in the Azure portal. And this is my dashboard view. This is the home view here. You can see I can have my favorites. I can create resources. I can view all of my resources. And we have a sidebar menu, and then we have the front menu. So there's 2 ways you can configure this. If I go into create a resource, I can search for what I want to do. Here's OpenAI. And I can then choose it from the list on the marketplace, and I can find the different resources I want to create. Next up, we have our notifications bell. This is anything that goes on, and while you're working in there, you'll get notifications. And then we also have our settings, and then reporting trouble and feedback are all across the top. I can even open up a command line and interface with my applications directly inside of the Azure portal. Everything is in a resource group, so you can sort by resource group, and you can see that those are lifecycle containers, and we have many resources inside of one, and you can delete them all together if you want to. And that has been a quick tour of the Azure portal, how we create resources and how we delete them. Here we are in Azure AI Studio, and we're going to explore the content safety features. And the content safety works against one of our other items. So here we've connected to our Azure AI multi-services account. And so note before we start, some of this content might be offensive because that's what we're looking for. So this is our text analysis. And so we put in some easy breezy text and we get, this is allowed because it was we know in advance that what this text already has in it. Let's try something that should fail. So this is a violent content. Again, we don't need to read it what it is. We know what the result should be. There it is, it's blocked. But what if we change our tolerance and we are more permissive? So this is going to give you a good idea of what's happening. So here I have a threshold. My threshold is higher. I'm going to be more allowing. We're going to do the violent content again. We're going to run the test, and this time it's allowed. So this is a great way to test your content filters against text you might experience to see what the result would be in your applications or in your AI solution. In this session, we learned how AI models are created with machine learning and neural networks. We discussed the many types of AI models we can include in our solutions and how to access AI in Azure. This concludes session 1. There are many ways to continue your learning journey. We encourage you to watch other videos in this course or search out your next favorite topic on Microsoft Learn at aka.ms/learn. I hope to see you next time.